Welcome to the fourth video in the Measure Theoretic Probability series. And in this video, I want to start actually discussing some of the content. This will be really some more preface, but anyway. So what we're going to do here, or at least what I'm going to talk about, is to give you a motivation for why you would want to study measure theory in order to then study probability theory. And the answer that I have for this is, well, for one thing, I do want to emphasize that it's not strictly necessary. Lots of statisticians do good productive work and don't use measure theory in their day-to-day work. Usually statisticians will have, seen at least some amount of material that is, relevant from measure theory, but they don't worry about the details and they don't really need to know that much, right? They can kind of just leave it to the professional mathematicians to worry about the sort of like rigorous proofs and formalisms. But there are some problems that really just cannot be understood completely without the use of the tools of measure theory. And what I'm going to do in this video is present one simple toy example. Because it is simple and toy, then it's not going to seem like a very real world problem. But I am going to suggest that the problem that we encounter in this toy example really does occur in applications. And in particular, I know for a fact, as I speak right now, that some mathematicians are, very heavily using the tools of measure theory in order to demonstrate the occurrence of gerrymandering in our United States political process. So it certainly does come up in applications. But here we'll just, for the sake of simplicity and kind of making the point, we'll discuss this toy example. And the toy example is going to be Bertrand's paradox. So let's get started. Let's explain Bertrand's paradox. Start by drawing a circle of radius 2 and inscribe inside of it an equilateral triangle. The radius doesn't really need to be 2, could be anything, but it'll make some of the numbers come out cleaner if we take it to be 2. Now we ask a probability question about this. And so we ask, what is the probability that, my abbreviation here, WITPT, I get tired of writing, what is the probability that? So what is the probability that a randomly drawn chord will be longer than an edge of the triangle? Let's just recall what a chord is. A chord is any line segment which has both of its endpoints on the circumference of the circle. And so to help us to sort of talk about this, let's say that a chord is long if it is longer than the edge length of the triangle and short otherwise. Now, what we're going to do to get a paradox is we're going to give 3 mutually inconsistent answers to this problem. And at the end, I'll suggest that measure theory can resolve that paradox. So let's get a first solution. The first solution is going to be 1/3. Let's see how we get it. So start by noticing that if a chord emanates from one of the vertices of the triangle, then we can identify whether it is long or short, depending on whether it falls inside or outside of the triangle. And to help us to sort of like analyze that, we can draw the tangent line running through this point and think about the angles that these chords form with the tangent line, right? So if the angle formed by the chord and the tangent line is between 60 degrees and 120 degrees, and this because the triangle we had said was an equilateral triangle, therefore the angle at any vertex is 60 degrees. And so we can see that if the angle is between 60 and 120 for the chord, then the chord is a long chord, otherwise it's a short chord. That means that the probability of a long chord is 60 divided by the total number of degrees available, which is 180, and that reduces to 1/3. So we have a first solution. By the way, if anybody is wondering, is this really valid? Because we did assume from the outset that the chords emanate from a vertex of the triangle, but not all chords You're right. You might think not all chords do, but even if you just draw a random chord, we can then spin the triangle so that a triangle vertex lies on top of an endpoint of the chord. And whenever we do that, we don't change anything about the chord. That's just a device to help us to analyze some of these other geometric facts about it. So this is a valid solution. Okay, let's move on to getting a second solution. And in this second solution, we're going to demonstrate that the probability is equal to 1/2. So this time we consider a chord that is running parallel to a triangle edge. And let's depict it. Let's assume that it's on the same side of the center as that triangle edge. So here in the diagram, I am drawing the triangle edge towards the bottom, and these chords are on the same side as that edge relative to the circle center. Now, having depicted it this way, we could reason that chords again are long if they intersect the triangle and short otherwise. And in this case, that means closer to the center than the triangle edge is, right? So chords that are closer to the circle center are long chords. And so we can, to help sort of mathematically analyze this, we can draw a radius that runs perpendicular to both the chord and the triangle edge. And then we can see that if the places where they intersect, the radius, if the chord intersection is closer to the center than the edge intersection, then it's a long chord. And then using basic high school geometry, we can demonstrate that the triangle edge bisects the radius that we drew. And that means that half of the radius corresponds to long chords and the other half to short chords. So that shows us that the probability of a long chord is 1/2. Okay, let's move on to a third solution. I mean, already that's enough, right? Two inconsistent solutions. That's already a paradox. But because these are a little bit fun, let's just do one more. Why not? And so in this solution, we will again draw the chords as parallel to some edge and on the same side as the center. But this time we make the observation that we could take the midpoint of the edge and spin it in a circle and reason that a chord is long if its midpoint lies inside of that swept out circle. And now the probability of a long chord is essentially the same as the probability of its midpoint being randomly chosen to be inside of that circle. So now we take the ratio of the areas. Oh, right. And I think I said earlier that we take the radius to be 2. I think here I have now switched over to taking the radius equal to 1. Well, no big deal. I guess my numbers don't come out quite as cleanly as they could have if I had been consistent about that. But in any case, it's clear enough, right? No matter which way you do it, the probability here comes out equal to 1/4, right? So if we say that the radius is 1, then the midpoint of the radius, right, the inner circle has radius 1/2. And then we see that the inner circle has area pi over 4, whereas the entire circle has area pi. We take the ratio of those two and we get 1/4. So that gets us a third answer. Now, finally, I just want to suggest how measure theory might help resolve the paradox. And of course, I can't say everything because we haven't yet studied measure theory, and so you don't know all of the tools and whatnot that we could use in this application. But I at least want to give some suggestions. So what's going on here is that even somewhat unbeknownst to ourselves while we were solving the problems, we were introducing a certain random generating process for the chords. So if you think about the first solution, you can imagine that it corresponds to a process of generating the chords where you pick any point on the circumference of the circle and then randomly pick any other point and form the chord between them. That looks a whole lot like essentially what we were doing in the diagram for that solution. In the second solution, we could identify that with a random generating process for the chords, where you pick a random radius, then pick a random point on the radius, and then draw the chord that runs through that point perpendicular to the radius. And in the third solution, you could view that as identified with a process of generating the chords by just picking any point and then finding the chord that has that point as its midpoint. And so it turns out that each of these random generating processes, in some sense, distributes chords, different kinds of chords, with different densities. And it's really that density that is responsible for these different answers. And measure theory will allow us to understand those densities, and in particular, will allow us to use them to get probabilities that should agree with the solutions that we've found here. And so that is some illustration of the sense in which measure theory is needed for us to really, richly capture these sorts of probabilistic processes like is coming in this problem.